应该这是一个
这样子，
也是这样，
这边这样去的。
Any fool can know the point. 有没有放你的那个枕头上面？
还没有教到那边。
还没有在那边。你接那个，你妈妈几岁？
哎，加上没有人嘞？
怎么样？可以在吗？
可以在哪？
可以，
可以。
要出吗？
阿弟哦，
上次看阿弟，
没有啦，不是啦，
但没有啦，没有分录
有顶子
啊？
顶子。
我还没去我们写情况。
哦，对哦，你的顶子，现在我知道。
看我对吗？看没有？佛学会做那个，做那有个入学会佛学会，主挺现实的，什么还什么现出你的原型。
给那个房间打先。
哎，没有，关键不是，这还不是不是，你没有四个大不是。哎，今天又看了一遍，为这个来修佛祖。哪一个是你的第一名？
不懂哦，那个考试。
你感觉？
也是懂哦。
我讲打了几分？好了，是出来，你看我都。记得，然后呢，要必须死前面。
还有来，不对了，哎，中间你放这个的，跟这个喂，
我要按对了，我在等这个稍微烈一点，我就直接换抹茶了。因为之前一开始是点换这样看对，然后我是这种，然后蛮快就有认定的。按摩砂，我闲置房间。我要买了，我在等我这个水的时候拍先。就是不是显示爽吗？你看看你那个不熟，我没有玩 game，我没有玩 game 啊！你不要讲啊，我没有玩 game，我没有玩 game 啊。看看你这个换了好像还是原本的？
原本的。
诶，你买了那个？
没事，没事。
你不是买一个笔头吗？你家？
哦，笔头我还没有用，这个还没有坏。
不要这样讲自己。
这个还没有坏。
哎，还好嘞。可是那个时候为什么你的那个时候这样出啊？
是没？他现在有一点那个了。
没有，之前我不懂，我不懂是你旧啊。
哦，已经没 six 了。他以前有一点，他写久了也是有点磨。
是啊，他那个时候真的是你出到
可能
还有东西吐出来。
哦。
那个时候了，那个时候是我。
所以我现在在 recording 而已。
Okay, hello my friend.
完蛋了，我考虑前面几分钟，看这个傻肥，傻肥还在那玩这个。
太贱，太贱。我不觉得有人看前面的，因为我看女朋友都是拉前面5分。所以什么？啊，笑你不会啊，笑你会不会啊？更简单的，我可以有个关系。Yes，也会导致也反正真的，所以讲这个里面哦，这个对，都没办法，大家有到这个。那你就用厘米啊，它这样它其实是用公正的，它是不是啊？它叫我来变厘米啊。我想看你，虽然它厘米是一了，但是我是说它是每一个东西，我跟他讲，所以我知道它去到最大不止3到。然后我是一个女生，你知道是在地方，但是你不明白这样，我一开始我就不懂。MP 推出来了，厘米ของ那个 constance， 是那个 constance， 我忘它。所以我是说它的那个就是不是这个，因为有些不 constance 分解是没有清楚，但是你这个是它就是有这种系统。但是它的项不同嘛，它一样是它我这第二是，我知道的可是你现在在做模，你是13吗？那个那个 BN 啊，是 BN，BN 是这个亚马的1是吧？B1 是这个然后 B 那有 B2是什么？啊，20。所以如果 D 是1了的话，如果你还要这个里面一不擦掉就好了。OK， 好。And then 如果是 B2的话，就是2减2，and then 2加3就哦。如果 n 的3减1，保住3.21加4加6，可是6是0，但是你要跟的。对，
对啊，
还有5分钟。觉得没毛病。在那里你们先这样子啊，这样，我这个BN 变成 B 啊，把这个 B 变成 B，所以B2啦，从2开始啦，这边咯，所以2减1是2啦，所以220，OK 好，3的话就1 2啦，and then 3减2 1加4 3 4嘛，这4加5不是9，
9啦，所以9才有啦。
还有一个是10。
OK，好 ，OK，好 ，OK，好 ，and then， so 你 pick up 这些E的 term 嘛，然后 and then，
然后我如果要找到，我要建立一个sequence 这个建立一个 formula 就是所有的，这样我可以不用这样写，是可以全部都一个，但是它不是
，and then，
我就有里面的跟你，然后我就可以
想想，没有，你要想象啊，你看这个 formula 是这样哦，它是一个 AN 的 formula，and then 你放0，它就要丢从哪开始？从1开始，从1开始的话，它就要丢这个东西，2的话，它就要丢这个。如果像你这样子的话，我给你0，你就要给我这个；你给我1，就要给我这个。然后你说，
肯定你是指如果你给我1的话，我就用这个你给我，就是用这个用这个
对
上面的
对。所以你现在你的做的法是把E，对咯，你分 K 说。感觉
对，等等，
感觉不是我们要的东西，不太像是我们要的风格的，就是，可是我又不知道讲跟你讲，我想一下有什么问题。现在你只是好像跟我讲说，n 如果大过一些，比如说类似可能说 n 小于10拿这个 n 大于10拿那个，因为你这是跳，对吧？但是如果我觉得你发一个习惯，但是你要干嘛呢？你要拿这个习惯来做。
你是讲我定这2个习惯了，就是要证明它是divergent，
对，为什么divergent？你这样子解读？
因为它是
infinitely many，
就是造一个它不会去，就是魔术，然后这里会去，因为时间。
OK， 等一下我再跟你讲，等一下再聊。我大概懂你要做什么，但是你好像没有那个正确的那个工具来。但是我觉得我知道你要什么，等一下我再跟你讲。Okay, ready to start? Okay, so good afternoon to everyone. So do you have any question from last week? Tutorial? Yeah? No question? Right, okay. Yeah, so please do your tutorial question, right? So I won't check your homework, but you can send me and have feedback if you want. Okay. Yeah. 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 Okay, prove that it is an increasing function, is it? Okay, so we haven't touched that part yet. We just introduced the definition last week. So let's see after this lecture, try again. Okay, if not, we come back again. Okay. Okay, so I'm not sure how you learn mathematics, right? Okay, so in university level, mathematics is quite different. Okay, don't just expect to use formula, okay, or just apply formula, just calculate. Okay, you need to know why is it true. Okay, how to use. Okay, why we can use it. Okay, what's the structure behind the theorem or the question? Why the question asked like that? Okay, what's the question asking? Okay, so that's why I put out this phrase here. Okay, anyone of you start thinking about project already? Not yet. Okay, yeah, try throughout the lecture, try and figure out what thing you are interested in. Okay, so for the reference, right? Okay, maybe maybe we will talk more next time. Okay, next time. Okay, let's go into lecture first. Today only got 2 hours. Okay. Yeah, so recall what we did last time. Okay, let's recall what we did last time. Okay, so we introduced what's the increasing sequence, what's a non-decreasing sequence, decreasing sequence, non-increasing sequence. Okay, so for increasing, decreasing, there are strict inequalities. Okay, strict inequalities, but non-decreasing and non-increasing are just inequalities. Okay, so you can imagine one of them as a staircase. Okay, where sometimes you get equal terms. Okay, but the other you can think of it as a slanted slope. If a sequence is increasing or decreasing, okay, it is a strictly monotonic sequence. Okay, and if a sequence is non-increasing or non-decreasing, then it is a monotonic sequence. Okay, so why we are interested in this? Because we are going to introduce a monotonic convergence sequence. Okay, but before that, we'll talk about this boundedness. Okay, so hopefully you already see that I posted out assignment. Okay, please start and look at the assignment now. Okay, don't leave it until the last minute. Okay, if you don't know the question, it's fine. Okay, please meditate on the question. Okay, meditate on the question. Think about it. Okay, think about it. Okay, some part I haven't touched yet. Never mind. But for those I already teach, you try, see if you can make it. Okay, if you cannot make it, you can discuss with friends. You can ask me also. Okay, but make sure you write down the collaboration statement. Okay, you collaborate with who? Okay. 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 So one of them involve these bounded definition. So please learn this boundedness. Okay. So when is a sequence bounded above? When is a sequence bounded below? Okay, when they are bounded above and below, then it is a bounded sequence. Okay, whenever we say a sequence is bounded, it is bounded above and below. Okay, above and below. Okay, it's within a range. Okay, so we are ready to go through the monotonic convergent sequence theorem. So what's the monotonic convergent sequence theorem? Okay, the theorem says that every bounded and monotonic sequence are how is convergent. Okay, every bounded monotonic sequence is convergent. Okay, so you can think of this monotonic sequence either going up or going down. Okay, anyhow, we don't impose strict condition. Okay, can go up, go down, whatever you want. Okay, but it is bounded. Okay, bounded above and below. Okay, bounded above and below. Then it converge. Then it converge. So last time I leave you with one question, right? Not sure how many of you think of this. So for a bounded monotonic sequence or monotone sequence, does it necessarily that the limit equal the limit equal to one of the bound? Does it necessarily that the limit equal one of its bounds? Does it make sense? What is my question is? Okay, so let's say, for example, if my sequence is monotonic, so I cannot come down, right? So maybe I go up, and then it's bounded. Okay. Does the sequence have to converge to the bound? One of the bound. Maybe I let you discuss with your friend. Maybe spend 2 minutes. Yeah. Try discuss with your friend. If yes, how to prove it? If no, can you give an example? Any idea? Any idea? Yes or no? No. Why? What can you do? What are the few example you have seen before? Sequence 2 plus. Oh, you mean this? 2 plus 1 over n. Okay. How about just 1 over n is enough? Okay. And 2 is just shifting out, right? So maybe just look at 1 over n. Okay. So what happened to 1 over n? So remember our sequence start with n greater or equal to 1. Okay. So we have 1 and then half and then so on. Right. Correct. And you can see that this sequence is actually bounded. Bounded by what? Bounded above by what? Above by 0? You sure? Bounded above by 0. Okay, bounded below by 0. Bounded above by what? 1. Okay. So from here, or from calculation last week, this sequence converges to what? 0. Okay. Which means it converges to one of the limit, right? Okay. But what can I do? Since it's bounded below by 0 and 1, right? I can just enlarge the bound. Okay. So similarly, I also can say that this 1 over n is bounded above by 2, bounded below by -1. It also works. Then in this case, none of this number is the limit of the. Okay. So in other words, what I want to say is depend on how sharp is your bound is. Okay. So the bound might not be your limit. Okay, depend on how sharp is the bound. Okay, yeah. So to get a sharp bound is also one important issue or job in mathematics. So mathematician has been working hard to decrease the bound, okay, on some object to get a better solution. Okay, yeah, because sometimes they cannot solve it, but they try to reduce the bound. Okay, so that we can see how far we can go. Okay. 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 Next. Okay. So let's go to your example of increasing function. Okay, just now. What's your name again? How to spell? K-E-N-G. K-E-N-G. Zhengkang. Okay, okay. Okay. Yeah, so just now Zhengkang asked about how to show something is increasing. So we will see in this example here. So let's show that this sequence is increasing. Okay, what is this sequence? This sequence is n over n plus 2. Okay, and then we will address the question whether this is bounded or not. Is it bounded? Okay, so to show a sequence is increasing, what's the definition? What's the definition? N plus 1 is strictly bigger than n. Okay, an. Okay, so okay, so to show n over n plus 1 is increasing, we need to show that n plus 1 term is strictly greater than the n term. And for all in n, or n start with 1, right? The other class will start with 0, so it'll be confusing. Okay, so show that this is true. How to show this is true? Why? Okay. Okay. So in other words, okay, good. So in other words, we can show that the difference between an and difference between an plus 1 and an is greater than 0. Okay, we want to show this. Okay, so why is this helpful? Why is this helpful? Why I want to do this extra stuff here? I can combine the two terms. Then how do I combine the two terms here? I can use I can make the denominator the same. Okay, I can first make the denominator the same. So what do I get here? So one of them I have n plus 3. The other one we have n plus 2. Okay. So to make the denominator the same, we just multiply a different factor to each side. Okay, so to complete the to make two terms, to make two fractions have the same denominator. Okay. What is this? What is this term here? Can anyone try to expand this? Try to expand this. So n square plus 3n plus 2 minus n square minus 3 over n plus 3. Sorry, or minus 3. Yeah, thank you. Okay, so you can see that actually some terms cancel out. Okay, so n square cancel out, 3n also cancel out. So you left with 2 over n plus 3, n plus 2. So is this last line true or not? Huh? Why is it true? Why is this true? Yeah, so why the left-hand side is always greater than 0? Or when does it true? When is it true? Because n is bigger or equal to 1. Okay, so this fraction is always greater than 0. Okay, it's always true since n is greater. Okay, so you can go from this last line and recover the first line. So the first line is true. Okay. Yeah. Okay, so this is based on the assumption of our n. Okay, this is where we use our n. Yeah. Okay, so attention an is increasing. Okay, an is increasing. How about boundedness? How about boundedness? So one side should be obvious. One side should be obvious. Okay, so whether is it bounded below obvious or bounded above is obvious? Bounded below or bounded above is obvious. This is an increasing function, right? So which one is obviously true? Bounded below, right? Because you need to start somewhere and then go up. Okay, so it's bounded below definitely. Bounded below by what? 0. Can you make it sharper or not? 1. You sure? Bounded below by 1, what is this? So our sequence is like this, right? This is what? This is not true because 2 is less than 0, so it's a contradiction. Not bounded below by 1. Bounded below by what? 1 over 3. Okay, 1 over 3 is what? Is the first term. Okay, right. So you are you're already abstracting the idea here. So increasing function is always bounded below by the first term, right? Because a1 is less than a2, a2 is less than a3. So you can form a chain of inequality there. Okay, a1 is the lowest one. Okay, so one thing we can see is an. Okay, so suddenly I come out with this an, right? So let's call our an. Let's call our an to be my n over n plus 2. Okay, so the sequence an is bounded below by a1, which is 1 over 3. Okay, since the sequence is okay, but we want to know whether it's bounded, right? Bounded below is not enough. Is it bounded above or not? Yes. Why? Bounded above by 1. How do you show it? How to check? How to check whether it is bounded by 1 or not? Put the limit. What's the use of the limit? Huh? Sorry. Range of n. What do you mean by that? Range of n is a natural number, so. Huh? What? So I mean, so the question is, does there exist an m? Okay, m. The question is, does there exist an m such that an is less than equal to m for all n? Is it bounded by something or bounded above? What? Why? How to show? Okay, and then okay, and then okay. Let's say you show the limit is equal to 1. Why? How does this tells you this sequence bounded above by 1? Convergent. Okay, convergent. Is that enough? Is a monotonic increasing. Okay, you also need monotonic increasing, right? Because in principle, right? Okay, in principle. So in principle, right? So let's say this is 1. Okay, how's your sequence converge? If I converge like this, can or not? Can, right? If it's not increasing, I mean, I don't care about increasing or not. I just care about conversion to 1. Okay, then the bound is different. But now your sequence is increasing. Okay, so it's always going up and then converge to 1. Okay, so there will be no hump like this. Okay, camel back. Okay, you cannot have this kind of situation. But I think there's a more straightforward method to see, right? Can you straight away check this or not? Can you straight away check whether n over n plus 2 is less than or equal to 1? Can you straight away check this? What is this? This implies what? N is less than equal to n plus 2. And this is always true. I think this one is more straightforward. Right. Okay. Okay. Yeah, don't think that any number put here will work. Okay. You can try. Okay, try 0.5, try 2. Okay, see which one work. Okay, it doesn't always work. So there's some choice involved here. Okay, there's some choice involved here. Okay. Yeah, so the limit answer, right, is what I did before last time I showed the class. So let's go through the limit argument. Okay, so the limit argument is like this. Okay, so we try and check whether our AN converge or not. Okay, whether our AN converge or not. If it's converging, again, then it's surely bounded below by the limit, right? Because our sequence is increasing. Because your sequence is increasing and then converge. Surely this sequence is bounded above by the limit. Okay, so this is the limit argument. Okay. Okay. Does everyone understand? Seng, are you confused? No. Okay. Please ask. Okay. Sometimes I see you guys face a confusing face. I know one. Okay. Yeah. Okay. If cannot digest, ask. Okay. So, what's the limit here? So let's compute limit of my an, n over n plus 2. Okay, so how on earth are we gonna compute this limit here? Can do or not? How many methods we learned last time? How many methods we learned to compute a limit of a sequence? We find the real limit of a real function, okay? And then we use the property of the limit, okay? And then we use a continuous function. Remember, if we have a convergent sequence, and then we apply continuous function to this convergent sequence, it also converges to f to the limit of the sequence. Okay, this is like the sequential continuity for a function. Sequential continuity. Okay, so what we can do to this first? Can we straight away use those things or not? X over x plus 2. What's the limit of x over x? 1. How to compute it? Okay, so let's try the first method, right? Okay, x over. So how to compute the limit of this? By 1 over x. Okay. Okay. And then what can you do? Okay. 2 over x go to 0. Okay. So did your calculus one tells you can bring your limit into this function? Did your calculus? You don't remember? I also don't remember. I never taught calculus one before. Let's hold this for a moment. If someone interested, maybe I can go and check this. Okay. But I can bypass this. Again, I don't want to go into this real business so fast. So let's play around with my sequence first. Okay. So I do the same trick to my sequence. Divide by 1 over n on both numerator and denominator, where I get 1 over 1 plus 2 over n. Okay. Okay, but now I got the property of limit of convergent sequence, right? So 1 is a constant sequence that converge, obviously. How about 2 over n? 2 over n also converge. Okay, so all these 3 sequences here converge. So I can bring my limit into my fraction or sum. Okay. So, so by so since 1 and 2 over n converge, so convergent sequences. Okay, we can apply the property of limit of convergent sequence. Okay, so what do I mean by that? That means that I can bring my limit all the way into the fraction and addition. Right, remember limit operator is linear. Okay. Are you confused or not if I put 1 or 2 over n, but I say it's a convergent sequence? Why a number is a sequence? It's a constant sequence. Okay, or you take all n. Okay, take all n. Okay, so we see this as a sequence now, not just some random number. Okay. Okay. In total, we'll get 1 over 1 plus 0, which is just 1. Okay. Yeah, just 1. So what? So this implies that AN is greater or equal to 1/3 and less than 1. Okay. Why? Because it's increasing and then converging to 1. Okay. So you can't have AN is greater than 1. Okay. Okay. Did you notice something here? I put a strict inequality here. Can anyone see why AN cannot be 1? Huh? Because it's a no, you can reach your limit, right? Because if you take a constant sequence, the limit is just that constant. It can be the same. So why AN cannot be 1? Sorry? And real number we cannot what? Why not? 1 is a real number, right? Why not reach real? N plus 2 is always greater than N. Good, right? So how we really write this down? How we write this down? Okay, how we write this down? Yes, so you can suppose. Okay, so let me write. So not that AN cannot be 1. And suppose on the contrary, AN is equal to 1. Okay, which means what? N over N plus 2 is equal to 1. Okay, which means what? N equals to N plus 2, which means what? 0 equals to 2. Okay, which is a contradiction. Okay. Similarly, you also can try another contradiction. Okay, suppose over. Okay, if you really don't want, are not convinced why AN is less than 1, you also can suppose AN is greater than 1. Right? Or greater than 1. What happens if AN greater than 1? Huh? You cannot have 0 greater than 2. So if N greater than 1, so N over N plus 2 is greater than 1, then N is greater than N plus 2. Sure. Okay, sure. Yeah. Okay, cool. Okay, this one also work. But another level I want you to think about is from the point of a limit point, for a viewpoint of limit. Okay, for a viewpoint of limit. Okay, for a viewpoint of limit. Y cannot be greater than 1. If there's a n such that an greater than 1, what's going to happen? This is an increasing function, right? So for n plus 1, n plus 2, n plus 3, it's going to be even further away from 1 already. Correct or not? Correct or not? Think about it. Okay. So if so when I talk about this number, right, please think about a ruler. Where is 1? Where is an? Okay, you need to give yourself a ruler. Where is 1? Where is an? So if an is above, let's say above 1, okay? How about an plus 1? How about an plus 2? I already proved that my sequence is increasing. So it's always gonna be increasing. Okay, so this means what? The limit of this sequence is even further away from 1. Correct? And this contradicts my limit computation again. Is it true? Just now I said that the limit of AN is 1, right? Okay, so what's the definition of convergent to L? Know how? So how are we sleepy today? What's the definition of convergent to L? What does it mean by a sequence to converge to L? What's equal to L? Yeah, so what does that limit equal to L means? I'm asking about definition. Why do I write limit of AN equals to L? Something arbitrarily close, something large enough. Carry it off. Yeah. There's one guy, one person. How about Larry Kong? Who is Larry Kong? Yeah.
For any given large enough n.
Yeah, for large enough f, and AN converge to L. So you can see, so you see, AN large enough is away from 1. Would it still converge to 1 or no? No, right? No, right? So this contradicts to our computation just now. Okay, so this also doesn't work. Because we know that our sequence is convergent. Okay, so AN cannot be greater than. Okay, no? So one idea I want to throw to you is when we say a sequence converge to L, meaning that L kind of pull every turns in the tail of the sequence together. Okay, you get what I mean? So you have an infinite sequence, right? Okay, when we get to the tail of the sequence, if we converge, that tail how to say um arbitrarily close to the limit. Okay, so you can think of that limit is like trying to pull everything at the back together, okay, as close as possible. So if this sequence go away, right, then this is not limit anymore, right? Because it's away from 1 already. 1 is not the limit anymore. Yeah. Okay. Yeah. Okay. So you should think of a limit as a magnet. Okay, magnet. You know magnet or not? Magnet. Okay, so pull everything at the tails together. Okay. Yeah, as close as possible. Yeah, arbitrarily close. Okay. Okay. So yeah. So we spend a lot of time. So hence our n over m plus 2 is product. Okay. Yeah. Okay. So what should I say? Yeah. So if let's say just now we didn't go through this limit computation here, right? Okay, we just use this simple inequality to check. Okay, so we know that it's bounded. Okay, we know that it's increasing. Then you can use the theorem. Okay, about monotonic sequence theorem, convergence theorem. That this sequence is convergent. Okay, this sequence is convergent. Converges. This sequence converges. Okay. Let me see what else we want to do. Okay. Now it's 242. Do you want to see one more example? Actually, only one more about one computation example and one abstract example. Maybe I give you choose which one you want to do, and then the other one will left as a homework. You want to do computation or you want to do some abstract nonsense? Okay, abstract. Before we jump to next topic, take a break. Which one you want to choose? Yeah, choose a abstract one. You want to choose a computational one. Pick one. Make a choice. In your life, you need to make a lot of choice. So please learn to make a choice now. Abstract. 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 Others agree? Agree. Abstract. Okay, good. I also like abstract stuff. Okay, let's do abstract. Okay, good. So let's do abstract. Okay, suppose that you know this is a little bit similar to what we have discussed, but let's have a look. Let's suppose you know that AN is increasing. Okay, it's an increasing sequence. Okay, and then you know that AN lies between 1/3 and 1. 1/3 and 1. Okay, 1/3 and 1. Thing is increasing, so my word gone increasing. Okay, sequence, and the terms are all in between 1/3 and 1. Okay, so explain why the sequence has a limit. Okay? So I already tell you there's a limit, so explain why. And what can you say about this limit here? Okay, I'll let you think about 2 minutes. You can talk with your friend. Yeah, explain why this limit exists and what should be the value of this limit. Okay, you need all 2 pieces of it. All the AN is bounded below by 1/3 and 1, and it's an increasing sequence. What can you say about this? Yeah, try and some yeah. Don't know. Why the sequence has a limit? So as I said last time, right, in mathematics, so whatever information given to you are very important. And you need to think about how to use this information. why I don't give more information, why I don't give less information. Okay, then this will tell you what is enough to get your answer. So there are two things here: increasing bounded. So why got limit? Because it's increasing. Ceiling and the floor. So bounded above and below. Okay. And then increasing is what? It is monotone sequence. Okay, so you have bounded, you have monotone sequence, so it is convergent. Okay, so if converge, then it's gonna limit. Okay. So since it is bounded sequence by the monotonic convergent sequence. Monotonic convergent theorem. It converges. And what do you say about the limit? Limit of this value of the limit. What do you mean? Okay, maybe you need more information to get the exact limit. How about the range of the limit? Strictly or not? Strictly or not? Huh? Strictly? Which one is strictly? Why 1/3 is strict? Because it is a increasing. Even if you start with 1/3, okay, your sequence is increasing. Okay, it must be aware from 1/3. How about 1? Can be equal. In fact, we see the example just now. It's actually equal to 1 for some of the area. Okay, just now we see one example. Okay, yeah. So of course, if I just put less than equal to, it's still correct. Okay, it's still correct. Why? Because the statement is all. All meaning if equal is wrong, less than is strictly less than is correct, then the statement is still correct. Okay. So in logic, if I just put less than equal, it's still true. Okay. So a bit sloppy. But if I put like this is a sharp. This is sharp. Okay. Okay. Yeah. Okay. Okay. There's an exercise in your pre-read notes, or maybe I just copy it down. Then you can do it as a homework. So homework. Show that the following sequence an and defined by a1 equals to 2, an plus 1 equals to an plus 6/2, and greater. Okay, is convergent. Okay, I already tell you it is convergent, so please show it why is it converge. And then find its limit. Okay, yeah, try to do this yourself. I'll put out solution in the lecture now. If you have problem doing it or understanding, you should come back again next lecture. Okay. Is it Clear? Okay. So let's take a break until 3 o'clock, and then we will come back for series. Yeah. Okay, let's take a break until 3 o'clock, and then we'll start with series. Let me take attendance. You are free to leave. Go to toilet. But I want to take attendance. 多黄页 OK 无有言 OK 谨慎 Lee Chen Jet Ivan Gan Sling Larry Kong. Larry Kong, are you from Sarawak? Oh, you're from Sarawak. Okay, because this Kong is like very familiar surname. Is your family originally in Sarawak? Okay, sure. Lo Hao. Lo Hao, yeah. Zhong Yi. Okay. Xi Qiaodong. Okay. Okay. Tang Zhengkan. Yi Xing. Okay. Shan Elinor here. Han Wei. Han Wei. Okay. Li Shui. Hey, who is sitting beside you last time? Rohan. Is there anyone sitting beside you last time? Is that? Huh? Oh, you don't know her. You don't know her. Stranger. Oh, I thought you guys know each other. Don't know. Okay, that's fine. So you are Sydney, right? Han Yanru. Okay. Liao Ruolan. Han Wei. Zuo Jing. Yu Xiang. Okay. Who's teaching your algebra again? Liu Jie? Huh? This semester? Huh? Yeah, now. Oh, Ali. Sorry? Ali. Ali quite new. Newer than me. I think not too bad. Well, I mean, I think I heard some your story with you, but I'm not sure how it happens. So how to say? Do you guys try to communicate with Liu Jie or not? No. See? Yeah. I think you guys should tell him, okay, what you how to say? I mean, what is your concern? What is your concern? Okay. Because learning pure maths is really quite a different how to say, different culture. When I first do pure maths, I was also shocked. Yeah, I mean, we are not just calculating, but we need to write a lot of essay, like proof. We need to write essay. So I was also not used to it, but I also get through it. So we also complain our first year calculus teacher, like, I mean, so how to say so go back to my first meme. I mean, if you don't want to listen, you can sleep, but I just say what I want to say. So yeah, so go back to this meme here. I said any fool can know, the point is to understand. Okay. So from my observation, my understanding to this kind of teacher is they don't quite know what student know or don't know. Okay, because they only have one set of working inside their mind. It actually works, but the, the assumption or the problem is you need to know what is going on first. If you don't know what is going on, what is he using, then you will be blur, super confused. The more he said, the more you confused. Okay, because sometimes he's just telling the true fact, but your brain is asking why, this is true, why this is true, why are you using, why the thing you use is true. Okay, maybe he think that that's trivial and then he just pass it. Yeah, so you need to tell him or ask him. Okay, why is this true? Okay, why are you using? Okay, why this line follow? Right. Okay. But maybe I don't know, but maybe okay, some lecturer will be like attitude not that good you say, this you also don't know. But please bear with it. Please bear with it. Okay? Because I have seen worse lecturer than you. You know, I go and met I go meet the office hour. Okay, we meet at 2, but he left at 2. I go and knock his door, there's no one there. Yeah. So he like run away from this. So this is even worse. So as long as the teacher are willing to talk to you, so you please learn as much as you can. This is what I would say. Okay, learn as much as you can. Okay, different teacher have different abilities. You can learn different stuff. For those that are not good, you don't learn them. Okay, throw it away. Learn what is good. Yeah, that's all I would say. But anyway, keep communicate with the lecturer like me. Keep communicate with me because I might not know what you want or you don't know. Right? So yeah, just email me or message me. Yeah, I'll just talk to you. So if you're scared to talk to me in person, right? So you can ask others to talk to me. Maybe. That also works. Okay, but anyway, try to communicate with your lecturer more. Yeah. Careful. Maybe we'll wait until Yixian to come back and then we'll start. By the way, if you look at the pre-read notes or somewhere that I didn't address the question or what, if you want me to address again, you can ask me. Okay, because sometimes I maybe accident or sometimes I purposely pass it. But if you have question, you just ask. Okay, or question from anywhere also can. Okay, like the tutorial question, what also can. Okay, so just ask if you are unsure about it. Okay. If you're unsure, you just ask. And I'll try to help. Yeah, where's Yixiang? So long. Maybe we will just start then. Okay, let's start with a series. Probably we will spend quite a long time on series. Yeah, is it okay? You okay? Sick? Okay. Okay, let's look at series. Okay. The series we are interested about is an infinite series. Okay. So infinite series is the series that is more interesting because if it is finite, right, you can just add up all the terms. Okay. So the thing that's interesting is the infinite series, which is we can add until a infinity. Okay. A infinity is not a term, it's just a shorthand notation. So sometimes we denote it as a sum. Okay, sum from n equals to 1 to infinity of an, or simply sum of an. Okay, infinite series. It is finite, you can just simply add them up. You get a number, right? Okay, either it's large or small. Okay, but how about infinite series? Do you always add up to an infinite number or not? Okay, not quite true. Okay, sometimes converge. So for example, okay, let's look at one example here. If I add a half plus 1/4 plus 1/8 plus 1/16, okay, what do you think this sum is? Is it converge or diverge? Okay, I haven't introduced this word yet, but is this equal to some finite number or infinite? Infinity. Finite number? How to find the finite number? Is it finite, right? So why is it finite? Why is it finite? Converge to what? To zero. How to converge to zero? You have some non-zero terms adding up together, right? So how to go to zero? Cannot go to zero. Last term, sure, last term converge to zero, yeah. But my question now, okay, so the problem or the difference between what we did with sequence is with series is now we try to add up term inside the series. Okay, we add them up. Okay, we add them up. So if we add them up, what's the sum here? Sums are just finite number. But how do you find a finite number if you understand it's finite? What's the pattern of this? Huh? What's the pattern of the term here? Multiply by 1/2. Okay, so which is what? What's this? I think you see this series before, right? Geometric progression. Okay, well, how to find the sum to infinity? Sum to infinity, how to find? Do you remember a formula or not? 1 a over minus r. So what is a in this case? So first term is a half. What is r? The common ratio. In this case is 1/2. So the answer is 1. Okay. So one way to think about this question is you have a 1. Okay. You have a 1 line, okay, 0 to 1. So you start with half of it, right? You start with half of it. Okay. And then you start with another half. Okay. And then you start with another half. And then you start with another half. And then keep going in. Can you see that this is trying to fill out the length one string here? Can you somehow see it geometrically? Can see? Can you imagine or not? I think, how about Yan Ru and Roland? Are you lost in my word? You lost? Okay, so what do I do first? So I take a string. So first I take a string of length 1. Okay. I don't care, this is even 1 cm, 1 meter, or 1 km, just length 1. Okay, regardless the unit. So I cut it into half. Okay, I got a half here. Okay, I take this half. Okay, I fill in this half. Okay, and then I fill in 1/4. What is 1/4? Half of a half. Meaning I can cut the other half into half again, and then I fill it in. And then I repeat the process. Half of a half of a half. So 1 in. And then I keep filling in the string here. Can you see that this is trying to converge to the whole line here? If I manage to fill all the half. Okay. So that's why these are called geometric progression. Because geometric series can be think of geometrically. Okay. Okay. Next time I will let you see more example of this geometric series. Okay, next, let's go on first. So we see that a series can converge. I mean, can get some finite sum. Okay. So how do we precisely say these things? Okay. So I want to relate series back to sequence. Okay, how to get sequence out of series? Okay, how to get sequence out of series? So this is what I'm going to do. So define the term of n partial sum. Okay. So n meaning the nth one. Partial is like half. Okay, so how half is it? So I'm going to define this. So n partial sum of an infinite series an, sum of an, or we denote it as Sn. So I denote n partial sum as Sn, not denoting this. Okay, so I put a comma here. Okay, so this is referring to the important nouns here, n partial sum. So it's given by n is equals to a1 at a2 up to an. Okay, or in other words, we truncate our sum at n. Okay, we just add up to n, up to an. I mean, okay. So in this case, what is S1? What is the first partial sum? What is S1? S1 is just A1. It's just the first term. Okay. And then what? And then S2 is A1 plus A2. And then S3 is A1 plus A2 plus A2, and so on. Okay. So these form a sequence. Do you see that this form a sequence or not? You add 2 numbers together, you get a number. You add 3 numbers together, you get a number. Okay, so this number form a sequence. Okay, let's play around with the sequence, right? Okay, let's play around with the sequence. So, for example, let's try one example here. So we're gonna start with a easy elementary result, okay, from your high school or your secondary school. So what's the n partial sum formula for a geometric series? Anyone can recall? What's the formula? Oh, I'm writing here. Anyone can recall? Anyone can recall? Yeah. Okay. So it is a times 1 minus r to the power n over 1 minus r. Okay. So this is the formula. So how are we going to show this now? How are we going to show this? How are we going to show this? How are we going to show this? Sorry? All terms multiplied by r. Okay. So why would we want to do that? Okay. So let's see what is given here. Okay. What is given here? Let's see what is given first. Okay. So what we want to show is Sn equals to a times 1 minus r to the n over 1 minus r. Okay, so this is given. Right, this is given. So this kind of statement, right, is already giving you a clue to. Okay, so this kind of statement gives you a clue how to prove it. These two things are equal. Okay, maybe we can try and play around with this equality here. Okay, in other words, 1 minus r times Sn equals to a times 1 minus r to the power n. Okay. Okay, right. Okay, so let's think about this statement here. Why is this true? Why is this true? Okay, why is this true? Why the left-hand side is equal to the right-hand side? If we manage to show this is true, then we'll get the first line. Okay, I agree. So to know the equation, right, of course you need to know what is left-hand side, what is right-hand side. Okay. I think right-hand side is pretty clear. It's just number n multiplied by 1 minus r also number n depend on what n. Okay. So it's some number. But on the right-hand side, left-hand side is what? You have 1 minus r is a number. Sn is what? Sum of number. Okay. What kinds of sum is this? Okay. Let's look at what is the left-hand side, right? So how can we write down this Sn? Sn by definition is what? The n partial sum. Okay, n partial sum is a1, a2, a3 up to an. But this Sn here is special. It's a partial sum of what? Partial sum of what? Of geometric series. Okay, so you can govern. Okay, govern the pattern of a1, a2, a3, a4. So what's the pattern? What is a1? It's just a. Okay, what is a2? ar. a3? ar squared. And then keep going on. Okay, up to ar n minus 1. Okay, good. So be careful, n minus 1 here, because we start with 0. Okay. Okay, so we know Sn. On the right hand side, what do you have actually? You have 1 and minus r. Okay, minus r times Sn. Okay. So am I allowed to write like this? Sn minus r times Sn. Allowed. Can write. Okay, because it is finite. Okay, finite. In particular, I can just put 1 minus r here on every term. Okay. And then what I do, I can expand. And then I collect the one with r, the one without r. Okay. So in this case here, we still need to know what is minus r. times n. Okay, what happens if we multiply minus r times n? So every term will be multiplied by minus r. Okay. N. Okay, how about I introduce an extra term? AR n minus 1 and minus AR n. Okay. So what can you observe here? Can you observe anything here? Cancellation. Okay. So in particular, what happened? You shifted the terms, okay, up by degree 1 of the R part. Okay. And then you introduce a sign on every term. Okay. So if I'm gonna add these two sequence together, I will just get the first term and the last term, which is a minus a to the r to the. Okay. In other words, what is this? This is just a times 1 minus r to the n. Okay, so this is giving what we want. Okay. Okay. Yeah. So this is the formula for the n partial sum of an infinite series or a geometric series. Okay, sure. Okay, sure. So I want to let you see the example we have just now. So let's go back to our example just now. Half plus 1/4 plus 1/8 plus 1/16 and so on. Okay. In fact, I can write this as sum of infinity of 1 over 2 to the power n. Okay, which is 1. We have proven just now. Okay, I want you to see it from the partial somewhere. Okay, how to see it from the partial somewhere. So let's see what is S1. S1 is just half. Okay, how about S2? Half plus 1 over 4. Okay, which is 3 over 4. And then S3 is half times 1 over 4 plus 1/8, which is 7 over 8. And then keep going on. Okay, keep going. So what is Sn? Oh, not 1. Not 1. N minus 1 over n. 2. Okay, so you mean you are using the formula, is it? Or what? Not yet? Okay, let you guess first. Okay, what you want to guess? Okay, so how do you get this? Okay, by the pattern, okay, by pattern, but how you prove it? Yeah, just use the formula. Okay, just now what we proven. This is what we proved, right? So just use this. So what is this? So this is half times 1 minus 1 over 2 to the power n over 1. And then you can see that this is the answer, which is 1 minus 1 over 2. Okay. Yeah. So if we take the limit, okay, so this is a sequence, right? Okay, like in the previous chapter, we look at sequence, we want to check whether this converge or not. Okay, we want to check this converge or not. Let's take limit. If the limit exists, then probably it converges. So what is this? How to take limit of this sequence here? Can you see that this is the difference of two convergent sequence? One is a constant function. 1 over 2 to the power n also converge. Okay. Converge to where? 0. Okay, converge to 0. So what? So we can bring the limit into the difference. We can bring the limit into the difference, where we get just 1. Okay. So you can see that this 1, right, also represent the sum to infinity. Okay. So what am I trying to say is, you can see that the inference series has a finite sum, okay, if the partial sum converges. So partial sum is a sequence, so we can say whether it converges. Okay. So an infinite series has a finite sum if the n partial sum converges. Okay. So sometimes we will say the infinite series converges. Okay, what do I mean by that? I mean that the n partial sum converges. Okay. So from the infinite series, we can cook out a sequence. How to cook out a sequence? You consider the n partial sum. Okay, n partial sum form a sequence. Okay. So from a series, we get a sequence. Can or not? Does it make sense? We start with an infinite series. Okay, how to get a sequence? We consider the n partial sum. S1, S2, S3, S4. Okay, which is what? A1, then A1 plus A2, and then A1 plus A2 plus A3. Okay, if you can't remember this example here. Okay, we start with X1. Okay, A1 plus A2, A1 plus A2 plus S3. Okay, until Sn. Okay, and then we look at the limit. Okay, if it converges, okay, if it converges, it will be the sum of your infinite series. Okay. Okay, I didn't get this example. Okay, so let me write down what I said just now. So definition. So a series, an infinite series has some, let's call it as a sum, as a finite sum. Let's call it S infinity, okay? If the if it's okay, if it n partial sum converge to S infinity. Okay, so now we link series and sequence together. Okay, so that's why we study sequence first, then we have series, because we need sequence. Okay, see here. Okay, so so maybe one property is important here. So let's give this property of geometry series. So the geometry series don't always converge, okay? So if you still remember from what you had last time, okay, when does a geometry series converge? It doesn't always converge. Okay, when does it converge? When can you apply the formula? It converges only when the ratio, okay, the ratio is strictly in between 1 and -1. Okay, yeah. Otherwise, like last time we said, right, when r greater than 1, if you take higher power, then it averages. Okay, so if it converges, okay, if it converges like what we said just now, the sum is really just A over 1 minus r. It's really just a over 1 minus r. Okay, so other than 1, other than r less than 1, the absolute of r less than 1, the geometry series diverge. Okay. Yeah. So let's quickly do one example. Let's quickly do one example here. So try and determine whether this series converge or not. So it's the sum of 2 to the 3 power n, 2 to the power 3n times 3 to the power 1 minus n. So is this convergent or divergent? So you see, so we quickly use this how to say, language here. We ask whether a series converge or diverge, right? But converge or diverge usually stick on the sequence. Okay, so how a series is connected to a sequence? Hmm? Which sequence we are interested in? Huh? How to cook out a sequence from a series? Huh? How to cook out a sequence from a series? How many? How to cook out a sequence from a series? Huh? Just one slide ago. S what? Huh? Sorry, say louder. S what? S infinity. S infinity is only one term. So yeah, S1, S2, S3, S4, S5. What are these S? These are what? Partial sum. Okay, and partial sum. Okay, so can you determine whether this is convergent or divergent or not? Using the partial sum. So if the partial sum converge, then the series has a finite sum, all converge. If diverge, then the sum diverge. I let you try about 2 to 3 minutes. See if you can determine whether this converge or diverge. Does the partial sum converge or diverge? What? You're done. What have you tried? Diverge. Okay. Diverge. Okay. So how you guys try or did everyone got it or haven't got it yet? Haven't got it? What have you tried? What did you try? You mean S1, S2, S3? So what did you get for S1, S2, S3? Huh? S1 is 2 to the power 3. S2 over 3. And then 2 to the power 9. 3 over 2. Then how to see this whether converge or diverge? Find the formula. Oh, okay. Find the common ratio. Okay. Oh, that is bigger than 1. How about what did you guys do? Geometry series. So it's the same, right? Finding the common ratio. Okay. Yeah. So what's the common ratio here? What's the common ratio? That's a mistake. What's the common ratio? Wait, I mean, I'm asking about the common ratio, right? So what's the R? I think you can't quite see it from this series, right? Is there a common ratio you can read out from this series? From this sequence, I mean. Huh? 8 over 3, 8 over 3? Is it 8 over 3? No, right? Not quite right. Say again.
Is that the
Sure.
yeah?
Yeah, sure. So what's your AN? AN is 2 to the power of 3n, I think.
Times 3. Yeah. Calculate the a n plus 1.
Calculate to the AN plus 1. What do you mean by that?
Yeah, next one. This one is a n.
Oh, okay. So you mean look at AN plus 1. And then what are you trying to do? Oh, you divide them. Okay. Oh, okay. Yeah, sure. Okay. Yeah. Okay. You want to divide this. Okay. But what is this? Hmm? From textbook? What do you mean? But this dividing, what do you get? You just get your ratio between AN plus 1 and AN, right? But my ratio want to be in between SN plus 1 and S1, is it? Well, what's the ratio you are looking for? What's the ratio we're looking for? I think this is correct, I guess. This is the right ratio we're going to look for. So what is this? So let's compute what's this. AN plus 1 over AN is what? So 3n times 2 times 3 times 3 minus n times 3 plus. So we cancel. And then go to n 3. Okay. So maybe plus so this one cancel. 3. Oh, I got the 3. 3. Okay. Is that right? That's right. Okay, then this is the same as this one, right? Isn't it? Okay. Why say this is wrong? Okay. Let me see. Let me see. Okay. Yeah. Okay. Yeah. I think this worked, right? This worked. This worked. Let me see. Yeah. Does everyone agree with this answer now? Is it this one? Okay. So what's this R? Huh? Sorry. Yeah, this is not the partial sum. This is the A1. So this is the ratio for A1, A2, A3, A2, so on. Okay. So what we are doing here is where is our A1 first? Where's A1? Two to power 3, 2 to the power 8. Huh? Huh? So you put 1, right? You put 1 into n, right? So the first term is yeah, it's 8. Okay, so let's just try. So first term is 8. Okay, so from our calculation, right, A2 should be 8 times 2 to the power 3 over 3. Correct? Okay. So what is this? So is this the same as the number we plug in here? Same. So when n equals to 2, A2 is 2 to the power 3 times 2, 3 to the 1, 2. So it's 6 over 3. Same. Same. Because you got 3 here, you got 3 here. Okay. 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 And then you can go on. Yeah. Okay. So you can see that this is in fact. So S1 is A1 by definition. S2 is A1 plus A2. So you are adding up the n partial sum of geometric series. So just now we give a property that if a geometric series, okay, if a geometric series has first term A and the ratio is greater than 1, that means the sum, the series converge. Okay, or have infinite sum. Okay, yeah, converge. Okay, good. If you look at three notes, there's an applied question on drug. If you want to try, you can provide solution. Let's try another example here. Okay, let's look at another example. So look at another example. So look at this sum of n minus 1 to infinity over 1 over 4n squared minus 1. Okay. Try to show that this converge. That this is convergent by expressing the n partial sum as a telescopic sum. We will show at the moment what does telescopic mean, and then by this we will find the infinite sum. Okay. So that telescopic will mean that the sum collapses into 2 terms only. Okay, due to the cancellation in between. Okay, in the middle terms. Okay, let's see how does this happen. Okay, let's see how does this happen. All right, so since we want to look at partial sum, okay, what we should do is we have to look at S1, S2, S3, S4, and so on. Okay. One thing you can do to this is so telescopic means there's some cancellation in the middle term, but you see here, right? This n square is always positive, okay? And 4 times this positive number minus 1 should be always positive. Why? Because your n is greater than 1. So if you consider S1, S2, S3, S4, they are all adding up positive number. So how do I get cancellation? Okay. So one way to do this is to look at the partial fraction. Okay, we try to break this into partial fraction. Okay, so let's see. So how to break this fraction into partial fraction? Do you still remember? 2n plus 1 times 2n minus 1. Okay. So we factorize it. And you can try and find the constant am. Okay. So by solving this, right? Okay. Does every one of you know partial fraction? If not, then I won't explain further. We will just compute it. No one have question? Okay, so this is a partial fraction. So how to find AB? Okay, so the above is true if the below is true. Okay, so we can get rid of our denominator first. So what's your normal approach to this finding AB? What did you do before? Okay, so you use the root. Okay, you use the root. Okay, otherwise you can actually use inspection. Okay, just inspect. Okay, if I just use inspection, what do? I just guess some possible number and then I test it. So I can use inspection and then see that A should be half and then B should be minus half. Either way, let me check. So I think A has to be half, is it correct? I think A half should work. Okay, doesn't work. So A minus half, B half. Okay, we can check it. So if A minus half, B half, okay, you can see that left hand side there's no n. Okay, we want to get rid of n. So either one should get a minus. Okay, but why I put a half here? Okay, because there are 2 ones here. Okay, so by one of them is 1, one of them is minus 1. I want to get positive. So what should I do? So that's mean if I put A equals to minus half, I get minus half here. Here I will get minus half, but I get minus 1. So what to do? Swap. Okay, so we stop again. Actually, I'm correct at first. So okay. So in this case here, B multiply minus 1, I get half. Half times 1, I get half. Half plus half is 1. Okay. But this one is alternating on 2n, right? So they cancel. Okay. Yeah. So you can use inspection or you can go through the root method, also works. Okay. So sometimes to save time, you just use inspection. But make sure you check it. Okay. Like what we did just now. Okay. So by inspection, we can split our fraction into half times 2n minus 1 minus 1 over 2 times 2n plus 1. Am I doing something weird or not? Correct. Please help me check. I'm not sure I got split something wrong. Okay, I think correct. And then I can factorize 1/2 out and then leave with this. Okay. So what's this term here? Half time a difference. Right? Difference between 1 over 2n minus 1 and 1 over 2n plus 1. So there's a difference coming out here. Also, let's see, there's a magic going on here. So let's look at S1. Okay, so what is S1 here? S1 here is just 1 over 3. 1 over 3. Yeah, so 1 over 3 if we calculate from here. Okay, but if we look at the other way to express it, which is what? Which is 1 over 2 times 1 minus 1 over 3. Okay, 1 over 3 also. Okay, so you can see that this 1 over 3 come from a different way, but really they are the same way, but it's a different way. So let's see how this way will be more beneficial to use. Okay, let's look at S2 now. Okay, similarly, if you just go through the same method, okay, if you use the usual method, what is S2? Okay, S2 is A1 plus A2. Okay, A1 is 1/3, you compute already. A2 you can just use the traditional way you substitute it in, and then you compute something out. Okay. You can try to compute it. There's no harm, but I'm going to tell you a better way to do it. So since we can split up our fraction into differences, so we might as well write down what is A1 and A2 here. Okay. Actually, we already computed what is A1 already. So let's bring our A1 down. How about A2? 1 over 2 times 1 over 2 times 1 over 3 minus 1 over 5. Okay, so how is it beneficial here? You can see that the terms, the 1 over 3 terms cancel. Okay, the terms in the middle cancel. Okay, what you left with is 1 over 2 times 1 minus 1 over 5. Okay, which is just 5. You see, much faster if you do it this way than you go and expand everything and then make them into the same denominator and then you cancel, simplify, right? Okay. You should compute this and really see that they should get the same answer. Okay. This is in fact what we did in the partial fraction. Okay. Let's try one more. Let's try one more example, and then we will finish off with this example and then we'll go. This is 3. What is S3? So S3 is A1 plus A2 plus A3. Okay. So A1, A2, we already got it. Okay, so this is A1, A2. How about A3? 1 over 2n minus 1 first. So 2n minus 1 is 5. 2n plus 1 is 7. Okay, so you can see again. Okay, again 1. Again, 1 over 3 cancel, and then 1 over 5 also cancel. Okay, and then you left with the first and the last one. Good. Okay. Yeah. So how does this help? How does this help? How does this help? So let's compute Sn again. Okay. What is Sn in this case here? So what can you guess about Sn? What can you guess about Sn? So if you list everything out, okay, 1 minus 1 over 3 plus 1 over 3 minus 1 over 5 plus, and then go on and forever. And then you will stop at 2n minus 1 minus 1 over 2n plus 1. Okay. And then you will see that you are left with 1 and the last term, which is 2n plus 1. Okay. So what's this? What's this? This is just a sequence, no longer a series anymore. So sequence, can you check convergence of the sequence? Okay, so you check the limit, whether this limit converge or not. So If it converge, then we have a finite sum, which means our series also converge. So, hey, where's this n? N is at the bottom, right? Okay, yeah, n plus 1. Okay, so can we bring our limit in or not? Can, right? Okay, because this converge, this converge, this converge, this converge. This thing then, this doesn't converge. Okay, this doesn't converge. So how? So instead of looking at each of them, we can look at the whole thing. 1/2n plus 1. 1/2n plus 1 converge. Okay, so one converge, this whole thing converge. So we can bring limit into these three pieces. Okay. Okay, so we can bring limit in. So 2n plus 1. Okay, so what do we get? We get 1/2 times 1 minus 0, which is just. So this means that, this means what? This means that our series converge. Our infinite series converge. Converges, and the sum is just 1/2. Okay. Okay. Any question? Any question before we leave? So starting on when's our next class? Tomorrow. Okay, just tomorrow. Okay, so tomorrow we will start introduce different tests to test whether a sequence converge. Okay. Tomorrow what time? 1. 1 or 2? 3, yes. Okay, so late. Okay, yeah, 3 until 6. Okay. Okay, see you tomorrow then.